Hello, everyone. Just a reminder, I will be out for Friday, March 8th, so there will be no in-person class on Friday. This lecture will replace class for that day. So what we're going to cover is the beginning of Module 8. We'll continue with Module 8 when we come back from spring break. So let's get into Module 8 a bit. So Module 8 is about inverse trig functions. And we've seen these before, right? We did this back in Module 4 when we were first starting to talk about triangle trig. If we had a ratio, let's just say if we had a sine ratio of opposite over hypotenuse in a triangle, and we needed to figure out the angle that gave us that ratio, we would use the inverse sine function. So again, just to recall, an inverse function reverses another function by switching x and y. It switches your input and output, and that's how it reverses the other function. So it switches x and y. And if our sine, let's just say for this sine function, right, our input is an angle and our output is a ratio. Inverse sine is going to switch that input and your output. So you're going, instead of getting your ratio out, you're going to put your ratio into inverse sine, and you're going to get your angle of theta out. So inverse functions, you put a ratio in and you get an angle out. And so that's what an inverse trig function does. And again, you can do this for the other functions as well, right? So cosine of theta, if you put an angle into cosine, the ratio that you get out is adjacent over hypotenuse, which means our inverse trig function, we're going to put that ratio of adjacent over hypotenuse in, and you're going to get the angle that it came from out. And tangent, our other big three, if you put an angle in, you get opposite over adjacent out. And so the inverse trig function, you're going to put that ratio in and you're going to get an angle out. Notice in all of these, you put a ratio into your inverse trig function, you get an angle out. You just have to be careful that you put the correct ratio into the correct function. So for instance, if I put a ratio of opposite over hypotenuse into arc cosine, the angle that I get out is not going to be the angle that I'm expecting because I put a sine ratio into inverse cosine, which is going to be real confusing, and it's not going to give me what I want. So you have to be really careful and just make sure that you put the correct ratios into the correct functions. So arc cosine needs to have a cosine ratio inside. Arc tangent, inverse tangent, needs to have a tangent ratio of opposite over adjacent inside. Okay, so that's what our inverse trig functions do, right? We've done this before. And an inverse function reverses another function by switching x and y, but not every function has an inverse. In order to have an inverse, the original function needed to be one-to-one. How do you know if a function's one-to-one? Well, it had to pass the horizontal line test. That means any horizontal line that you draw has to hit your function at only one point. As long as every single horizontal line hits your function at one and only one place, you are one-to-one. If a horizontal line hits your function at more than one point, you do not pass the horizontal line test and you are not one-to-one. Really what this means is that your y's can't cheat. You can't have one y value with more than one x that belongs to it. If you do have a y value that's cheating, that has multiple x's, it's not one-to-one. Your function's not one-to-one. Okay, so we have inverse trig functions, right? We've used them before. So Our original trig function, sine, cosine, and tangent, should be 1-to-1, right? Well, wait a second. This is what sine of x looks like, right? This is y equals sine of x. We just saw this in module 7. So, but this isn't 1-to-1. Look, I have a horizontal line right here that hits my function in more than one place. It's actually going to hit my function at infinitely many places. This thing is definitely not 1-to-1, which means that sine of x should not have an inverse function. So what do we do now? Well, we are going to have to choose a restricted domain. This is what we do when our original function is not 1-to-1. But we need an inverse function. We choose a restricted domain where our function is 1-to-1 and our function also has to cover the entire range. So we've got two things that we have to be careful of when we're restricting a domain. Our function has to be 1-to-1 over that whole restricted domain, and our function still has to cover our entire range over that restricted domain. So let's see if we can find a place on y equals sine of x where we are 1-to-1 and we cover our whole range. So before we do this, we have to figure out what is the range of sine of x again? The range of this function goes from -1 to 1, right? We cover all the y values from -1 up to 1. So I'm looking for part of this function where I am 1-to-1, and I also have to cover from -1 to 1. Well, what if we just looked at the part of this function that went from -pi/2 to pi/2? Right in here, just this section of my function, just this piece. I'm 1-to-1 there, right? Any horizontal line that you draw over just that part of the function hits this thing at one place. This is in fact 1-to-1. And this part of the function also covers everything from -1 to 1. So this part of the function works. Is that the only part of the function that works? Is that the only possible restricted domain for this function? No, actually. I could also let me pick a different color here. I could also go from pi/2 to 3 pi/2, right? In this region, from pi/2 to 3 pi/2, this part of my graph, just this section of my graph, is also 1-to-1 and covers everything from -1 to 1. I also cover my range. I'm good there too. This section would work as well. So my restricted domain could be from pi/2 to 3 pi/2. But wait, that's not the only one that works. I could also pick from 3 pi/2 to 5 pi/2. This region also works, right? This section of my graph is also 1-to-1 and covers my range there. I could pick any of these, and these are not the only possible regions that work. I could pick any of these restricted domains. So, a long time ago, when our forefathers of math were figuring out how to have an inverse sine function, um, those old guys a long time ago had to pick one of these. And now we are stuck with the one of these that they picked. So the official restricted domain of sine of x is -pi/2 to pi/2. This is the domain that they picked a long time ago. These old guys picked this one. That is the restricted domain of sine. Again, that's not the only one that they could have picked, but that's the one that they did pick and the one that we're stuck with. So that's the restricted domain of arc sine. Well, of sine of x, so that we have an inverse function. What that means is that as far as our inverse function is concerned, this is the only part of the function that exists. It does not see this part. It does not see this part. The only part of this function that inverse sine sees goes from negative pi over 2 to pi over 2. This is the only part of the function that exists for our inverse to see. So then our inverse, our arcsine function, that's y equals inverse sine of x, or y equals arcsine of x. These two mean the same thing. Again, I'll just remind you that inverse sine and arcsine mean exactly the same thing. It's the same function. So these guys exist. And basically, we're going to take this part of the function and reverse x and y. So if I take my points on the function, sorry, I'm just going to remove some of that here. So my inverse, or sorry, my forward function here on y equals sine x, I have the point negative pi over 2, negative 1. When I reverse x and y there, I'm going to get negative 1, negative pi over 2. So negative 1, negative pi over 2. That's going to be an ordered pair here on my inverse, because an inverse switches x and y. Here I have the point 0, 0. When I switch x and y, that's going to go to the point 0, 0 here. And this point up here is the point pi over 2, 1. So when I reverse those, that's going to go to the ordered pair 1, pi over 2. So I'm going to have an ordered pair here at 1 pi over 2. And I will rewrite this one too, just so you have that one. Again, I'm switching x and y to get these ordered pairs. And what's going to happen is if you pick more points, you'll see that our function looks like this. This is what y equals inverse sine or arc sine looks like. Now, you don't need to necessarily know what the graph of this looks like, but I think it's helpful to picture this. And it's going to be helpful for us to find the domain and range, which is really what we are interested in here. So what is the domain of this arc sine function here? What x values does this cover? Yep, it just covers from negative 1 to 1, right? The only x values that we cover here go from negative 1 to 1. And then the range here, what y values are covered? This just goes from negative pi over 2 to pi over 2. That is the range here. And again, we include each of these because we have points here at the end. So this is what arcsine looks like. Again, you don't have to know what it looks like, but you do need to know what these guys are. And something that I want you to notice is that the domain of inverse sine is the range of y equals the sine of x, right? The domain of the inverse is the range of the original, and the range of my inverse function here, this is the restricted domain of y equals sine of x, right? The range of your inverse is equal to the domain of your original. But again, to have an inverse function at all, we had to restrict the domain of the original. So this is the only part of the function that sees. And so what that means is that when we're using inverse sine, the only angles that inverse sine is aware that exist go from negative pi over 2 to pi over 2. And we'll get into what that means a bit more in a bit. So this is the big important thing that I need you to know for inverse sine is the domain and range. And that's why it all works. Okay, so that's inverse sine. So we had to restrict the domain to have an inverse. What about cosine? Is this one 1-to-1? No, not one-to-one. Okay, well, that means that we have to restrict our domain. Okay, domain. Let's see if I can spell here. Okay, so we have to restrict our domain. Again, we're looking for a place on this function where my graph is one-to-one and I still cover the range. So again, my range here goes from -1 to 1. I need a section of my graph that is one-to-one that still covers that range. Well, I could go from -pi to 0, right? This section of the graph, right? This part is both one-to-one and covers my range. But that's not the only one. I could also go from 0. Here we go. From 0. I'm sorry. Switch colors. Technology is great. Okay. I could also go from 0 to pi. If this was my restricted domain and this was the only section of the graph that existed, then again, I'm one-to-one just in that area and I cover my range. That one would work. But that's not the only one. I could also pick pi to 2 pi. This section of the graph is also one-to-one and covers my range. It could be that one. So these aren't the only ones. We have lots of different restricted domains that we could pick, but old guys a long time ago decided which one of these that we need to use. And the one that those old guys picked was this guy right here, from 0 to pi. That's the one that the old guys picked, and that's the one that we're stuck with. So as far as arc cosine is concerned, this part doesn't exist. None of this exists. The only part of cosine that exists is this part, and that's the only part that it can reverse. So if I'm going to only have that section, then it goes from this point, which is 0, 1, to this point, which is pi -1. And along the way, we go through this point, which is pi over 2, 0. And my inverse cosine, my arc cosine function, is going to reverse those. So instead of going through 0, 1, this guy is going to go through 1, 0. Instead of going through pi over 2, 0, my inverse function is going to go through right here, 0, pi over 2. All right, I'll write these out. That's 1, 0. This point is 0 pi over 2. I'll write that here. 0 pi over 2. That's the ordered pair here. And it's also going to go through, instead of going through pi -1, my inverse function is going to go through -1 pi, which is up here. So this function is going to look like this. This is what arc cosine looks like. And again, as far as the curving goes, you could pick more points to see that. But for right now, I'm just asking you to hit the I believe button. Here's what arc cosine looks like. You won't be responsible for the graph, but I think it helps, especially with the part that you do need to know, which is the domain and range of this guy. So this is my arc cosine function, which looks like y equals inverse cosine or arc cosine. These two notations mean the same thing, so I just want you to kind of be aware of those. And the domain of arc cosine is, what x values does this graph cover? It covers from -1 up here to 1. So my domain goes from -1 to 1. And the range of this one goes from 0 up to pi. So this goes from 0 to pi. And again, note that the domain here, This is the range of y equals forward sine of x. And my range of my inverse cosine function, this is the restricted domain. Oh, sorry, I said sine here. This is cosine. Sorry about that. I don't have y'all with me to find my errors, so hopefully I find them all. Okay, so this is the range of forward cosine, and this is the restricted domain of cosine of x. Because the domain of your inverse is the range of your original, the range of your inverse is the domain of your original. But we had to restrict our domain to have this inverse. And so this, again, is the part that you'll be responsible for here. Those are the big ones. So between arc sine and arc cosine, I want you to notice the domains are the same from -1 to 1. Notice that our ranges are different. The range of arc sine goes from -pi/2 to pi/2. And the range of arc cosine is from 0 to pi. The ranges of these guys do not match, so be careful with that. We'll talk about what this has to do with anything here in a minute. But before we do that, we've got one last function. Tangent. Is this one to one? Does this have an inverse function? Nope. No inverse function here. Okay, well, not 1 to 1, which means we don't have an inverse, which means we need to restrict our domain. So what's the restricted domain here? We need to find a place where our original function is 1 to 1 and where it covers our range. So notice I could go from -3 pi/2 to -pi/2. Just this section, this little whoop-de-doo here, this is 1 to 1, and it covers my entire range from -infinity to infinity. It covers everything. So that could be my restricted domain. But wait, I could also go from -pi/2 to +pi/2. This piece is also 1 to 1 and covers my whole range. So I could pick that one. But I could also pick from pi/2 to 3 pi/2. I could pick this one. That is also 1 to 1 and covers my range. Again, there's a lot of these that you could pick, but we are stuck with the one that the old guys a long time ago picked. The one that they picked goes from -pi/2 to +pi/2. They picked this one right here in the middle. That is the section that they picked to restrict our domain to. That's what we're stuck with. Okay, so then the arctangent function, right? Y equals inverse tangent, or we can say arctan. These both mean the same thing. This one's a little bit harder, so I'm just going to pick a couple of points here, and I will reverse those. I'm going to ask you to hit the I believe button for me here for a second. Notice that tangent has vertical asymptotes at -pi/2 and +pi/2. When we switch x and y, those vertical asymptotes at x equals -pi/2 and x equals pi/2 turn into horizontal asymptotes at y equals pi/2 and y equals -pi/2. So those vertical asymptotes turn into horizontal asymptotes. This point 0, 0 goes to 0, 0. This point at pi/4, 1 goes to 1 pi/4. And this point here at -pi/4, -1 goes to -1, -pi/4. And I can kind of fill this in, and you can hit the I believe button. If you pick more points, this is what your inverse tangent graph will look like. Again, you don't have to know what the graph's going to look like, but we do need to know what the domain and range of this guy is. And I think the graph is really helpful to get those. What is the domain of this arctangent function? What x values does this cover? Well, I've got arrows here, so this goes all the way from negative infinity all the way up to positive infinity. This covers everything. And the range of this thing, the y values that this covers, goes from negative pi over 2 up here to pi over 2. But notice that negative pi over 2 and pi over 2 are horizontal asymptotes. I'm never actually going to touch it. I don't have points there, which means my range is from negative pi over 2 to pi over 2, but we do not include those endpoints. So these are the domain and range of arctangent. And just notice the domain of your inverse is the range of your original. And the range of your inverse is the domain of your original, but this is the restricted domain of my original because we had to restrict the domain in order to even have this inverse. Okay, so that is how this all works and how we construct inverse functions. Now, what does this mean? The fact that we have restricted domains of our original, and that means that the ranges of our inverse are restricted. What that means is that each of these functions only sees certain angles. This does not see all angles everywhere. Remember, arcsine goes from negative pi over 2 to pi over 2. This one. Arc cosine goes from 0 to pi. And arc tangent goes from negative pi over 2 to pi over 2. These are the ranges. So what that means is if we put angles on the unit circle, right? If we would graph angles in standard position, this is where 0 is. Here is where an angle of pi over 2 is. Here is where an angle of pi is. Here is 3 pi over 2. And back here gives us 2 pi. So that's both 0 and 2 pi. Now notice there's a negative pi over 2 here. Where exactly is negative pi over 2? Well, that's a negatively rotating angle. Negative pi over 2 is down here. So these are negatively rotating angles, some of these. So what that means is that arcsine goes from negative pi over 2, which is down here, to positive pi over 2, which is up here. It only sees quadrant 4 angles, the negatively rotating ones, and quadrant 1, positively rotating ones. That's arcsine. And tangent is in the same boat, right? Arcsine and arctangent both see from negative pi over 2 to pi over 2. They see quadrants 4, negatively rotating angles there, to quadrant 1, positively rotating angles there. So I'm just going to say, let me color code this. Actually, I should have done this in a different color. So arcsine and arctangent here, they cover this one. Sorry, I should have used color when I started. That would have helped this. So quadrant 1 and quadrant 4. That is what arcsine and arctangent see. Now on the other side of this, I will use, let's see, a different color here. I'll use this purple color. So arc cosine here, this goes from 0 to pi. 0 is here, right? and it goes all the way to pi, which is here. So arc cosine sees here, quadrant 1, positively rotating angles there. It also sees quadrant 2. And in quadrant 2, these are still positively rotating angles. Okay, so what this means for us in principle is that when I put a ratio into each of these trig functions, whether that ratio is positive or negative is going to determine which quadrant the angle that this gives us will live in. So if I put a positive ratio into inverse sine, a positive ratio of inverse sine in quadrants, arcsine can only see quadrants 1 and 4. All students take calculus. Notice that sine is positive in quadrant 1 and negative in quadrant 4. So that means if I put a positive ratio into arcsine, I'm going to get an angle in quadrant 1 out, because that's where angles that have a positive sine ratio live. And if I put a negative ratio into inverse sine, I'm going to get an angle in quadrant 4 out, and notice that it's going to be negatively rotating there. If I put a positive ratio into arc cosine, well, in quadrants 1 and 2, all of them are positive in quadrant 1, which means cosine is positive in quadrant 1, and it's negative in quadrant 2 because only sine is positive in quadrant 2. So the quadrant that's going to give me a positive ratio is going to be quadrant 1, and the quadrant that gives me a negative cosine ratio is going to be quadrant 2. So if I put a positive ratio into inverse sine, it's going to take me to an angle in quadrant 1. If I put a negative ratio into inverse sine, it's going to take me to an angle in quadrant 2. Okay, and then finally tangent. Tangent, arctangent, can only see angles from negative pi over 2 to pi over 2. All students take calculus says that tangent is positive in quadrant 1 and negative in quadrant 4 because only cosine's positive there. And so if I put a positive ratio into arctangent's going to take me to an angle in quadrant 1. And if I put a negative ratio into arctangent, it's going to take me to an angle in quadrant 4 because that's the only quadrant that arctangent can see, and that's where the negative ratios will live. And in quadrant 4, these are going to be negatively rotating angles. Okay, let's do just some of these to help you understand what I'm talking about with these. So we are going to figure out which quadrant the answer will live in, and then we're going to find the answer exactly. So let's just first do the quadrant for all of these. So if I'm doing the arcsine of the ratio 1/2, this is a positive ratio. When I put a positive ratio into arcsine, I get an angle in quadrant 1 out. So inverse sine of 1/2 is going to take me to an angle in quadrant 1. Okay, let's do the next one. If I'm doing the arcsine of negative root 2 over 2, I'm putting a negative ratio into inverse sine. So if I put a negative ratio into inverse sine, I'm going to get an angle out that lives in quadrant 4. And again, in quadrant 4, these are negatively rotating angles. Okay, let's do the next one. Arc cosine of negative root 2 over 2. I'm putting a negative ratio into arc cosine. A negative ratio into arc cosine is going to take me to quadrant 2. Okay, the next one, arc cosine of root 3 over 2. This is a positive ratio in arc cosine. A positive ratio in arc cosine is going to take me to quadrant 1. Hopefully you're picking up what I'm laying down here. This is going to tell us where the angle lives that this thing is going to take us to. All right, number 5, arctangent of -1. I'm putting a negative ratio into arctangent. A negative ratio into arctangent is going to take me here to quadrant 4. And when I go to quadrant 4, this is going to be a negatively rotating angle. And now arctangent of √3, this is a positive ratio in arctangent. A positive ratio in arctangent is going to take us to quadrant 1. Okay, so that's how we figure out which quadrant each of these is going to take us to. Now let's figure out how we can solve this. Okay, so let's come back to number 1 here. Arcsine of 1/2. So I'm looking for an angle, right? Because this is going to give me an angle. I'm looking for an angle in quadrant 1 that has a sine value of 1/2, because really this means that the sine of theta is going to be 1/2. So I know that the sine of this angle theta is going to be 1/2, and it has to live in quadrant 1. So what we're going to do, let me see if I can go back to where, oh, here, to this one. Let me see if I can, oh, it won't let me do it. Okay. I'm going to go back. There we go. Let's do this. 11, 13. Where did I put the unit circle? Here we go. This is what I'm looking for. Okay. The unit circle. We are looking for an angle in quadrant 1 that has a sine value of 1/2. So we're looking here in quadrant 1, and a sine of 1/2 means the y value should be 1/2. That angle is going to be pi over 6. So what's going to happen here? This isn't going to do that for me. Okay. How do I go back to? No. Sorry, y'all. I'm not very good at switching between things here. Okay. Oh no. Okay, let's go back. Sorry, y'all. Everything is hard here. So we're going to here. This is module 8. So we were looking for the angle in quadrant 1 with a sine value of 1/2, and that was pi over 6. After all of that technical difficulties, the angle in quadrant 1 with a sine, a y value on the unit circle of 1/2, was pi over 6. Okay, so let's work on number 2 here. I'm looking for an angle, right? Because when I put a ratio into arcsine, an angle is going to come out. I'm looking for an angle that lives in quadrant 4 that has a sine value of -√2/2. Well, I know that the angle in quadrant 4 here that has an ordered pair that has a sine value of -√2/2 here, this is going to be right here at 7 pi over 4, right? But this needs to be a negatively rotating angle. So the answer here is not going to be 7 pi over 4, because that does not live in -pi/2 to pi over 2. We need the negatively rotating angle, which is this one. Let's do this. Here we go. Everything is hard here. The negatively rotating angle here, which is negative pi over 4. The one that this is going to spit out is negative pi over 4. The negatively rotating angle there that has that sine value. So negative pi over 4 is our answer here. All right, number 3, arc cosine of -√2/2. This is going to give me an angle in quadrant 2 that has a cosine value of negative root 2 over 2. So you're going to go to the unit circle, you're going to look in quadrant 2, and you're going to look for the one that has a cosine, an x value of negative root 2 over 2. And you're going to find it here at 3 pi over 4. And that is between 0 and pi. That is the answer here. It's 3 pi over 4. You only need to do negatively rotating angles in quadrant 4. All right, next one. Number 4, arc cosine of root 3 over 2. I'm going to get an angle in quadrant 1 that has a cosine value of root 3 over 2. So I'm looking for the angle in quadrant 1 that has an x value of root 3 over 2. You'll find that here at pi over 6. This is a quadrant 1 angle. It's positively rotating. All right, number 5, arc tangent of negative 1. I'm looking for an angle in quadrant 4 that has a tangent value of negative 1. So in quadrant 4, you're looking for the angle that has a y over x value, right? Tangent is y over x. You're looking for the one where you take y divided by x and you get negative 1. And that's going to happen right here at root 2 over 2, negative root 2 over 2, which is 7 pi over 4, right? Y divided by x here, negative root 2 over root 2 over 2 gives us negative 1. But my answer can't be 7 pi over 4. That's not between negative pi over 2 and pi over 2. It's got to be the negatively rotating angle in quadrant 4, which is negative pi over 4. So that is going to be the angle that this gives me, negative pi over 4. And then the last one, arc tangent of square root of 3. I'm looking for the angle in quadrant 1 that has a tangent value of root 3. So y over x has to be root 3, or that's root 3 over 1. I like to write it out like this because that tells me that root 3 needs to go with my y value. 1 needs to go with my x value. So you're looking for the point on the unit circle in quadrant 1 that has root 3 in the y value and 1 in the x value, which is going to be this one. Actually, sorry, I'm trying to do this in my head really quickly and making mistakes. The x value is 1, which is up here at 1/2 root 3 over 2, right? The root 3 is with y, the 1 is with x. That happens here at pi over 3. And so that is the angle that this is going to give us. It's in quadrant 1, so we can leave it as positively rotating. Okay, that's where I'm going to stop here today. This is kind of a confusing process. So we're going to continue to fight through this and figure out how to evaluate inverse trig functions. So the big important thing here is that I need you to work on knowing which quadrant these are going to take you to, and then we'll use our unit circle to figure out what that angle is. All right, so I hope that helps with the start of homework 8. And I will see you after spring break. Be safe and have a great break.